Along with finding HCF and LCF, one more optional question asked in the paper is, show that every positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. They are telling that we need to show that every positive odd integer will be of the form 4q plus 1 or 4q plus 3. So how to proceed with this question? Very simple. This question is also based on Euclid's division algorithm, that is Euclid's division lemma. So we know that the generalized form of Euclid's division lemma is A is equal to BQ plus R, where R is greater than equal to 0 but less than B. This is the generalized equation for Euclid's division algorithm. Now let A be positive odd integer and B is equal to 4. Let us take A as the positive odd integer and the value of B is equal to 4. So if we apply this in the given equation, that is a general equation, it becomes A is equal to 4 into Q plus R. But we know that R is greater than or equal to 0 but less than B. That is nothing but R is greater than or equal to 0 less than B. Here we have taken the value of B as 4. So it will become B is equal to, it is less than 4. In the place of B I can write it as 4. So here this, let us take this as equation 1. Put R is equal to 0 because R is greater than or equal to 0 and less than 4. So it carries the values R is equal to 0, 1, 2, 3. It should be less than 4 but greater than or equal to 0. So let us take R is equal to 0. So the equation 1 becomes A is equal to 4Q plus 0. That is nothing but A is equal to 4Q. This is the answer we got. A is equal to 4Q. Now put R is equal to 1. Equation 1 becomes A is equal to 4Q plus 1. We got one more value for A. Similarly, if I put R is equal to 2, then it will be A is equal to 4Q plus 2. Now put R is equal to 3, then A is equal to 4Q plus 3. I got 4 values for A. In the beginning, we have assumed that A be a positive odd integer. Suppose if the value of A is equal to 4Q, this 4Q can be divided by 2. If it is divisible by 2, it becomes positive integer, positive even integer. So, and if it is A is equal to 4Q plus 2, then also it is divisible by 2 and it becomes positive even integer. So, but we have taken that A is positive odd integer. So, the value of A cannot be 4Q or 4Q plus 2 for odd integer. Therefore, odd integer is of the form 4Q or 4Q plus 3. So, how do we write this? Since A is an positive odd integer, it cannot be 4Q or 4Q plus 2. The reason is they both are divisible by 2. They both are divisible by 2. Therefore, any odd integer is of the form any odd integer is of the form 4Q or 4Q plus 1 or 4q plus 3. So this is the answer for the given question. One more question asked in the same question paper is, prove that root 2 is an irrational number. This question was asked for 3 marks. So how to start with the proof? This proof has to be done with contradictory method. I have already discussed to prove root 5 is an irrational number in my previous videos. You can just go through that and come back to this to get a better clarity. So let us start to prove this. So proof. As I told before, it should be done using contradictory method. That means we have to assume that root 2 is rational number and prove that our assumption is wrong. So let us assume root 2 is a rational number. Let us assume root 2 is a rational number. So if root 2 is a rational number, I can express root 2 as root 2 is equal to p by q. Rational numbers can be expressed in the form of p by q. So here the condition is q is not equal to 0 and p and q are, p comma q are positive co-prime integers. They are positive co-prime integers. Here co-prime means the common factor between p and q is 1. So common factor is equal to 1. So now if I take this q to left hand side, it becomes q root 2 is equal to p. Squaring on both sides. Squaring on both sides, I can write this as q root 2 whole square is equal to p square. So this square applies to both the digits, that is q square root 2 whole square is nothing but 2, which is equal to p square. I can rearrange this equation as 2q square is equal to p square. So I got the equation as 2q square is equal to p square. This is my equation 1, very important equation. So what does this 2q square is equal to p square implies is, it tells that 2 divides p square. So 2 divides p square. Now based on the theorem, we can tell that if 2 divides p square, then obviously 2 divides p. 2 divides p. Very important statement. So from equation 1 we were able to tell that 2 divides p square, and based on the theorem we are telling that 2 divides p. So this is my first stage. Next what we can write is, we can assume that let p is equal to 2c, where c is some integer. Now you can ask, why have we taken only 2c, why can't we take the other numbers? Because we have taken 2 here, is we have to prove that root 2 is irrational. I have to prove that root 2 is irrational, so I have taken it as product of 2. P is equal to 2c. Now I can substitute the value of p is equal to 2c in equation 1. Equation 1 becomes 2q square is equal to, in the place of p square I can write it as 2c whole square. Now 2q square is equal to, 2 square is 4, c square. Q square is equal to 4c square divided by 2. I have sent this 2 to right hand side. So after simplification, 2 1s are 2 2s are. So I'll get q square is equal to 2c square. This is my equation 2. Q square is equal to 2c square. What does this implies is, this implies that 2 divides q square. So based on the theorem, I can write the statement as, if 2 divides q square, then obviously 2 divides q. This is my second important statement. So in the first statement I have written that 2 divides P. In the second statement we are writing that 2 divides Q. So here P and Q has 2 as their common factor. P and Q has 2 as their common factor. But very interesting students, what did we assume in the beginning? We have assumed that P and Q are co-prime numbers, co-prime integers. That is, their common factor is 1. But what did we arrive here? We have arrived that P and Q as 2 as their common factor. So this is the contradiction for our assumption. We have assumed that root 2 is a rational number. If root 2 is a rational number, if suppose root 2 was a rational number, then the common factor should be 1. But here we are getting another number, other 2, which is the common factor between P and Q. So this tells that our assumption is wrong. Our assumption of root 2 is a rational number is wrong. Therefore, root 2 is an irrational number. This contradicts our assumption that root 2 is a rational number. Root 2 is a rational number. Therefore, root 2 is an irrational number. Hence, proved. So this is the proof for the given question. So these are the questions asked in the year 2019. Thank you, students.